Alright, Dalton's law of partial pressure basically describes a container that is mixed with several different gases, and so the total pressure of the container in this mixture is the sum of the partial pressures of each individual gas. So let's look at an example of this. So we have a mixture of O2, CO2, and N2. So remember, it states that if we have this mixture, it's going to be the sum of all these gases. So the pressure of oxygen, the pressure of CO2, and the pressure of nitrogen are going to be equal to the total pressure, or P total, of the container itself. Okay? And so then it goes ahead and gives us our numbers. So our total pressure is 0.97 atmospheres. And it says, what is the partial pressure of oxygen? So we're looking for the pressure of O2. If the partial pressure of CO2 is 0.70 atmospheres and 0.12 atmospheres for nitrogen's partial pressure. So to isolate the pressure of oxygen by itself, we are just going to subtract 0.7 and 0.12 from each side. And so we will find that it's 0.15 atmospheres. And that's the total pressure for just oxygen within our container and our gas mixture. So as far as Dalton's law goes, it's a pretty simple concept. Okay, we just have a bunch of different gases. Say we're looking at the oxygen, CO2, nitrogen, and all the other gases within the atmosphere or within air in a classroom. Okay, we can check the pressure within the classroom and then from there narrow down each gas based off of partial pressures. So we are going to look at Dalton's law added to what we've already learned with ideal and combined gas law. So in the beginning I told you when gases were first looked at, a guy named Boltzmann and Maxwell decided to collect gases and study their overall change when pressure, volume, temperature, and amount were altered. So how they collected gases was through water displacement, and how they studied it was through water displacement. So like it says in your notes, it is common to collect a gas by water displacement. So we have this water level right here, and as more oxygen is trapped or as more gas is trapped, the water level is going to go down because we have an increase in gas that's being trapped. However, some of the gases collected will include water vapor because it is traveling through water. So we must correct for this by looking up the partial pressure of water at that temperature. And this is given to us using a water vapor pressure reference chart. And I'll show you that in just a second. But what is happening in this picture is that we have some substance being decomposed. So for this picture we have potassium chlorate being decomposed or heated up with a Bunsen burner, and as it decomposes it turns into KCl and oxygen. So the oxygen that's being released is being collected by a stopper and a plastic tube. So the oxygen gas is going to travel through this tube and it's going to pass through the water and it's going to collect as gas within this container. And so as it travels through water, oxygen is going to include water vapor in here. And so like our note says, we have to take this into account to find out the actual pressure of oxygen. So let's look at that picture in a word problem. Okay, so we have KClO3 was heated in a test tube and decomposed. The oxygen gas was collected by water displacement at 22 degrees Celsius at a total pressure of 750 torrs. So as soon as you see that it was collected by water displacement, it's most likely that it includes water vapor. Okay, the volume of gas collected was 0.650 liters and the vapor pressure of water at 22 degrees Celsius. Alright, and it has a pressure of 21 torr. So the first thing we are going to do is calculate the partial pressure of oxygen, because it running through water, of course, is going to contain that water vapor. So we remember that P total is going to be the sum of the gases involved, so the pressure of oxygen and water vapor. So it gives us the total pressure of 754 torr. We are looking for the pressure of oxygen, and then it gives us the vapor pressure of water, which is 21 torr. Okay, so we want to find the pressure of oxygen by itself, so we are just going to move 21 over to the other side, or subtract 21 from each side, and when we do that we get 733 torr. Okay, so that is the first step, and then usually it says calculate the moles of O2 or calculate the volume or something like that. Well, since we see the amount of oxygen, remember we use the ideal gas law. Pressure times volume equals moles times the ideal gas constant times temperature. So we are going to move it around to solve for N, so PV divided by RT. Okay, so with this in mind, we have the pressure of oxygen, which is 733 torr. Okay, but remember, our R constants have to be in kilopascals or atmospheres, so we have to convert this to one of the two. I always convert to atmospheres because it's usually the most common standard pressure used. So I'm going to convert this using my standard pressure volume, or values, excuse me. Torr is going to cancel out, and we get 0.96 atmospheres as our initial pressure. So now we can continue on plugging it in. 0.96 atmospheres times our volume, and remember for ideal gas law it has to be in liters, which they already gave us, all divided by R. Since we're using atmospheres, we're going to use 0.0821 liters times atmosphere per moles of Kelvin times temperature, so we got to take 22 degrees Celsius and add 273 to that, and we get 295. So I'm going to put 295 here, and then now we just plug it into our calculator. In the end, you should find that N equals 0.0, I believe it is 258 moles. And that's our final answer. So here we're just taking Dalton's law and applying it to help us find the initial pressure of one gas, and then using ideal gas law, or we can even use combined gas law to help us out. Okay, so with this in mind, we can look at our simple Dalton's law of partial pressure by adding and subtracting. So go ahead, pause the video, do these two problems, and then press play and check the answers. Alright, so hopefully you did this before watching, but it's asking for the total pressure, so P total of the mixtures of gas, and basically we're just taking all of the gases they gave us, the 4 gases within this mixture, adding them together to find the total pressure. So I have 5 plus 4.56 plus 3.02 plus 1.20 kilopascals. And when we add them up, we should get 13.78 kilopascals. Okay? So then, for the bottom one, it says find the partial pressure of CO2. It's the total pressure, so we're going to put 30.4 kilopascals here. This total pressure is 30.4, and it's the partial pressure of the other two gases, so it's going to be added to CO2. So we are going to add 16.5 kilopascals and 3.7 kilopascals. And to isolate PCO2 on one side, we are going to subtract 16.5 and 3.7 on both sides. And in the end, you should have gotten 10.2 kilopascal. Right? So that's basic Dalton's law. So now let's look at what happens when you are not given water vapor pressure within the problem, and how Dalton's law applies to the combined gas law. So looking at part E on your unit sheet, you have the following are collected over water, which means that we're going to have to take out the pressure of water when we're looking at each individual gas. It says find the dry volume, so that means V2 at STP, so P2 and T2 are going to be at standard temperature and pressure unless otherwise noted. So the partial pressure of water vapor should be determined from the reference chart, and here is the reference chart given. Okay, and so that being said, let's look at number 1, 183 milliliters of gas at 16 degrees Celsius and 740 millimeters of mercury. So we are going to write this down. P1 that they gave us is 740 mmHg. V1 was 183 milliliters, and T1 is 16 degrees Celsius, which we know we have to change to Kelvin by adding 273, and we get 289 Kelvin. Alright, since we ran this through water, we are going to have to look at our reference chart and subtract the water pressure. So at 16 degrees Celsius, we have 13.6 mmHg and 1.82. Since we have millimeters of mercury as our starting unit, we are going to use 13.6 and subtract it from our total pressure to get our partial pressure of whichever gas we are actually working with. So 740 minus 13.6, we get 726.4 millimeters of mercury for our initial pressure. And then it says that we are looking for our dry volume, so that's V2 at standard temperature and pressure. Standard temperature is 273 Kelvin, and standard pressure of millimeters of mercury is 760. So now, since we're working with an initial and a final situation with no amount taken into consideration, we are going to use the combined gas law, P1V1 over T1 equals P2V2 over T2. So we are going to cross multiply to isolate V2 by itself. And so in the end, when we get V2 by itself, we divide by P2 and T1 on both sides, and our equation we are working with is P1V1 times T2 divided by P2 and T1. So we are just going to put in our values. So we have 726.4, which we found as the partial pressure, times V1, which is 183 milliliters, times T2, which is 273 Kelvin, all divided by the initial temperature, 289 Kelvin, times P2, 760 mmHg. Millimeters of mercury cancel out, Kelvin cancel out, and so our V2 value is 165 milliliters. Okay, so in this situation, everything is pretty straightforward, like the problem we've seen in our notes. However, occasionally they will give you a pressure that does not match any of the pressures on our water vapor chart. So let's look at number 5 on our unit sheet. Number 5 says 890 centimeters cubed of gas at 21 degrees Celsius and 1.10 atmospheres. So notice on our chart we only have millimeters of mercury and kilopascals. You can do this one of two ways. You either can take the value you find on the chart and change it to atmospheres, or change the pressure they gave you in the problem to mmHg or kilopascals. So I'm going to show you changing the initial number they gave you. So let me write down everything that we have. Okay, we have P1, which they gave us as 1.1 atmospheres. They gave us V1 at 890 centimeters cubed. And then T1, they gave us 294 Kelvin, or 21 degrees Celsius. Okay, and so then we know, of course, P2 is going to be whatever standard pressure we find on the chart. V2 is the dry volume we're looking for, and T2 is standard temperature, 273 Kelvin. So because there's only millimeters of mercury and kilopascals on our water vapor chart, I am going to go ahead and convert this to kilopascals by multiplying it by 101.325 kPa over 1 atmosphere. Atmospheres cancel out, and so our total initial pressure is going to be 111.46 kilopascal. Now I can look to see what the water vapor pressure is at 21 degrees Celsius in kilopascals. 21 degrees Celsius, kilopascals is 2.49. So I'm going to subtract that 2.49 right here, and I'm going to get 108.97 kilopascals as our initial pressure of this one individual gas. Okay, and so since I chose kilopascals, I'm going to use the standard pressure of 101.325 kPa. And from here, we just plug it into the same equation we used on the last one. V2 equals P1 V1 times T2 divided by P2 and T1. So initial pressure is 108.97 kilopascal times our initial volume, 890 centimeters cubed, times T2, 273 Kelvin, all divided by P2, which was 101.325 kilopascals, times T1, which was 294 Kelvin. Kelvin will cancel out, kPa will cancel out, and when we plug this into our calculator, we get 889 centimeters cubed. Okay, so that is the combination of Dalton's law with our combined gas law. Of course, if it's asking you for a dry volume where it says you're using water displacement to capture the gas, you have to take into consideration the water vapor and use Dalton's law to subtract the water vapor's pressure. Okay, so I suggest that you go ahead and finish up part E. Pause it here, and I will have the answers in just a second. Your answers for number 2 should be 1.89 decimeters cubed. For number 3, you should have gotten 244 centimeters cubed. And for number 4, you should have gotten 2.0 liters. Okay? So if you are struggling with this, come see me for tutoring, or go see another chemistry teacher for tutoring as well.